Hi folks, I'm Geek here. Unfortunately, they did not have the microphone on for the previous talk, and that continued on into this talk until about the 2-minute 37-second mark. At that point, you will be hearing Jim's beautiful voice. So hang out to then, and the talk will continue. Sorry for the technical inconveniences.
Got it. Now speak. Here. Now can you hear me? Okay, good. Start over. All right, we'll start over. We'll rewind. I'll stay here and come on back.
Yeah, stay exactly where you're at and don't move much.
Yeah, this thing is, there we go. Shh. Be very, very quiet. We need to start again, Adrian?
Well, just keep going.
Okay. So, one of the things that we want to look at is what kinds of things can happen when we're browsing the internet that give away our data. But recently, what happened in the news? What did Congress do for us that doesn't protect our privacy any longer, right? There was a Congressional Senate resolution that allows internet providers now to track your personal data and sell it for a profit, right? Okay? So this is all going back to there's a bigger story here that you'll kind of put the pieces together as we go. So what ended up happening here was these people started grabbing your data and they're starting to sell it as feeds. Now, when we're gonna get ahead here and look at what is EDNS, what is EDNS Client Subnet, and why is it important. So I can't move around too much because the microphone's really noisy. But what you see on the screen here is a packet capture from a single DNS query that has EDNS Client Subnet data in it. And the yellow highlighted part is the information that's being disclosed not only to your upstream recursive server, follow this logic, but to every server in the DNS chain all the way to the root server and every other server that's queried to answer that query. This is disturbing, right? Because normally in a DNS query, you would query an upstream resolver, and it would send a query out on your behalf if it couldn't answer from the cache. But the upstream queries from that server had no idea what your IP address was, okay? With EDNS Client Subnet deployment, that's no longer true. We're going to go over how all of that works. So normally we think DNS, we're getting a question to a server, we're getting an answer. we're moving on. We don't really think much about our DNS unless it doesn't work, right? So our goals for today, we're going to review a brief history of DNS all the way from the beginning. Long time back, some of you aren't even that old, so you won't know much about this because you were tiny at the time. We're going to discuss EDNS0 RFCs. We're going to look at how they came into being. We're going to explain one of those EDNS options. We're going to say what they are. We're going to examine one of those particular options that's in play, which is EDNS Client Subnet. We're going to look at some tools for how we would check DNS servers to see if they do support that, if we're getting responses or they're leaking data on our behalf. And then we're going to discuss some security concerns with that and look at some ways that that could potentially be abused.
Hello there, Eli here, and this is the Wayback Machine for traveling through time. And this is my boy, Chairman. Speak, Chairman. Hello. Good boy.
All right, so we're going to fire up the Wayback Machine and go on back here. Anybody know what cartoon this is from? Yes, bingo, you get the prize, Rocky and Bullwinkle. All right, so DNS was introduced in 1983. Came about as a research project under the ARPANET program. Initially, email was the first protocol used on the ARPANET, right? There was people just exchanging messages back and forth. As more hosts were added to the network, people had to have a way to know how to send an email to a particular host. Well, you all know what host files are, right? So those host files used to be the only way DNS worked. There was a key group of host files that were exchanged among servers. Somebody took care of those servers. If you wanted to add another server to your network, you had to go in and manually edit the host file. DNS was introduced in 1983 by Paul Macapetri and John Postel. They worked at the Information Sciences Institute at USC. The original RFCs for DNS are RFC 882 and 883. Both have been since updated in 1986. And the current RFCs for DNS are 1034, which describes the data structure for DNS, and 1035, which describes how the records and infrastructures are formatted when they're shipped over the network. So, in 1973, these files were kept in a central system that was called the hostmaster. So that's where you get the name hostmaster from in the internet. When you're talking about hostmaster that's why you would send a request to hostmaster to grab your DNS records and put them back on your server to update your server. All right, so DNS is a distributed database. Now, I want to make a distinction here. When I'm talking about DNS, I'm talking about the structure of the distributed database and not the service that manages that database. Right now, they're two distinct entities, and we'll get to both of them here. So the main components in the distributed database are the namespace. The namespace is defined as the layer in the tree where your records are stored. The root is the dot domain, okay, the dot domain. So anytime you do a DNS lookup with DNS lookup, that trailing dot is the root. That needs to be in your DNS query. Some servers and operating systems put it in there automatically. Others ignore it, but that's why it's always a DNS entry ends in a dot, because that's the root of all DNS, is the dot in that query. So they go back to the root or master domains. Each of the namespaces have resource records. They're called RRs, or resource records. And those resource records then tell what resolvers and name servers are allowed to answer authoritatively for that domain. And the original reason that DNS came out, conclusion was that, excuse me, my throat's a little dry here. That when DNS came out was to allow users to have a name to apply to an IP address, and that's John Postel's quote there. So this is what the DNS namespace looked like in 1987. It wasn't much bigger than this. It was a little bit bigger than this, but it really wasn't too big. So there wasn't too much to it at that point in time. So keep in mind, we needed to have a way to define what the way that the data was transferred between servers and how we're going to keep that distributed database up to date. So DNS came out and it did not really define anything other than the hostmaster files and servers that could exchange that data. Second generation DNS was improved by defining a master and a primary server, at least one master and several slave servers for DNS. It added the notify, so when a record changed in a DNS zone, you could notify the downstream host, and it added zone transfers, okay? So initially when DNS was put in place, if you changed one record in a zone that you hosted on your DNS server and you were part of the DNS chain, you had to transfer all your zones to the next neighbor. Everybody had to transfer all the zones. There was no mechanism to transfer just one zone meaning think domain, to the neighbor upstream. This brought in the ability to transfer one zone, one domain's set of data to upstream neighbors. And it also defined how the transfer would happen. It added a notify telling the upstream provider or the upstream servers that a change had happened, and that was linked to a serial number in the SLA record for DNS. Third generation made DNS even more optimized by implementing dynamic updates. This allowed a single record within a zone to be exchanged between DNS servers, so the whole zone didn't have to be transferred, just that one changed record. It also started, this is where we see the introduction of the mechanisms for EDNS0, which are RFCs 2671 and 6891. We'll come back to this here in a little bit, but this is the time frame that these were added. These last two RFCs were proposed by Paul Vixie. The fourth generation DNS added some clarifications for the structure of DNS, and it implemented provisions for negative responses, which are called NX domains. Fifth generation DNS implemented DNSSEC, which everybody knows kind of sucks because not everybody does it right. If everybody did it, it would work. Nobody does it right, especially the .gov domains. Anybody ever have a day where the .gov domains, their certificates expired and you're enforcing DNSSEC on their domains? That's always a fun one when our customers call and say, yeah, you're not resolving DNS for them. Yeah, their certificates are expired. They didn't rotate them. And it also promoted the use of these EDNS option codes, which we're going to talk about here a little bit more. Before I go on and talk about the EDNS option codes, I want to talk a little bit about the service that actually manages DNS, so a DNS daemon or service. Bind was the first one. It was funded by a DARPA grant at UC Berkeley. It was put together by Doug Terry, Mark Paintner, and David Riggle, and I don't know how to pronounce this guy's name. I think it's Zhao. And it was described in a paper in 1984. About 1985, Paul Vixie and ISC took over production of Bind, ran that as part of their contribution to the network community. And that company, ISC, still manages that service or that particular daemon. And Paul Vixie doesn't work for them anymore. He works for Farsight Security. The first internet daemon was Bind, but there are other ones that are in place now. Obviously, Active Directory DNS or Microsoft's DNS, Simple DNS Plus, Nomium, Unbound DNS Mask. Now keep in mind that some DNS servers can work as both an authoritative and a recursive or caching server. Others can only work as a recursive server. So Unbound, for example, it doesn't do any authoritative zones. It's just a simple caching server. Some of the other ones will do both. All right, so here's a couple references. If you want to go back and look at the history of DNS, there's obviously the book on the right is the manual, the Bible on DNS. One on the left is available on the internet, gives you a good overview of DNS so you can understand it a little bit better, explains it in fairly simple terms. So now we want to go on and look at these RFCs, 2671 and 6891. These RFCs now deal with the EDNS options, the EDNS0 options that were added to DNS. So these were proposed by Paul Vixie in 1999 and replaced by 6891 in 2013. So these are standards for allowing DNS zones or records to exchange data that are longer than 512 bytes, basically. Look at it that way. There came a time where certain types of information on networks, particularly Active Directory, now exchanged, they need record data that's much longer than what you could fit in a normal DNS packet. So now this provides a mechanism for text records, RRSig records, the things that make DNSSEC work, the kinds of records that are bigger than what you would normally see. It also defined a standard for adding certain features to DNS that we're not going to talk about today. It defines some transport standards, and it defines some options in the formats and assignments of these EDNS codes. So these EDNS option codes are defined within this EDNS0 specification. There's a long list of RFCs, and the next slide shows you some of the ones that are in place currently with IANA. The EDNS option code for Client Subnet is 8. Now, in play, there are about 12 RFCs in play and about 3 to 4 drafts in the works. And there's some other uses of these option codes that aren't even documented. Okay, so this is why I got involved in this talk. There's 65,535 different option codes defined within the EDNS0 options under these option codes. So that gives you the option to have 65,000 different types of data that can be transferred inside a DNS packet, either in or out of a network. Okay? What we don't know is what people are using those packets for that we're not monitoring or knowing about, right? They're there, that space exists, DNS servers will forward that data, they will receive that data. So we don't really know what's happening with the undefined or unused option codes in DNS. This is a screenshot from the IANA website, the section that defines EDNS0 option codes. They're known as opt. It's a particular type of DNS record, same as an A record, a pointer. An opt record has a certain structure and format. Oh, come on. There we go. Go forward. The option resource record format is this. If you look at the record, it's got a name. The name always has to be the root domain. Don't ask me why, but that's just the way they set it up. The part that's interesting is the very last record, the R data octet stream. That's where these name value pairs, the 65,355 different options, could go in this record stream as a name value pair. So here's the structure of what goes in that name value pair area. And you'll see that there's an option code, which is the number. In EDNS Client Subnet, it's option 8, but it could be 1 through 65,335. The length tells how many bytes are in the packet that it needs to look at, and then the option data, and I'll show you some examples of that. That's going to be the data that's specific for the RFC for that particular option. So this initial draft came out in, I believe it was 2011. It was called the Draft Vandergast EDNS Client Subnet 0. So the way IANA works and the ITEF is they give, when somebody requests the use of something particular or wants to make an addition or a change to a known RFC protocol, they first apply for a draft, and then it's got whoever the first author's name is in it, then the name of that draft or where it falls in the tree of that particular protocol. So in this case, the draft person's name, Vandergast, EDNS, and then Client Subnet is the name of it. Okay, so you'll see, you can search for RFCs that have dash EDNS dash in the names of them, and you'll find all the RFCs or drafts that come up that want to use these option codes to ship data back and forth via DNS. This was submitted by a couple of guys from Google, Verisign and Neustar in 2011. Really didn't get much attention. The second revision to it, interestingly enough, was submitted on July 4th, 2013. So I kind of look at that as like, wow, Independence Day, but they're taking away our independence to browse the internet. It just seemed a little ironic to me. The next draft was submitted they added some people from Akamai in 2015, and there's a very quick history here. Now, I put this in here because I want you to take notice. We go from, going back a slide, we go from 2011 to 2015 having the second draft put in, right? So it took it 4 years. Now, all of a sudden, July 6, 2015, Revision 2, Revision 3 in August, Revision 4 in September, Revision 5 in December, Revision 6 again in December. There was a mistake in Revision 5. Revision 7 came out in March, 8 in April, and the RFC was passed in May of 2016. How many of you knew that that became an RFC last year? Nobody, right? So, does this have a foul smell to it? When you see who's behind who's pushing this? Google, Akamai, a few others, right? The cloud DNS providers. We'll get to why they're doing that. Another interesting thing, which I searched for patents on these EDNS options. And I did find that somebody tried to submit to patent the use of this option both in the US and in Europe. That tells you how much they value these EDNS options and their use in DNS traffic. The patents are still pending. I don't think they're going to pass. I don't think they'll ever get anywhere, but they did file the patents, so we'll see what happens with that. So, how does EDNS Client Subnet work when a query is being resolved? Normally, a client checks, sends a query to its resolving server or its AD server, whichever one. It has a cache. It checks the cache, returns the result if it's there. Otherwise, it forwards it on to the next resolver upstream. Problem here. If the DNS resolver that you're querying supports client subnet, it's going to append your local IP address, or your machine's IP address in this case, to the DNS packet in the EDNS option 8, our data packet. It's going to send that up to the next server. The next server is going to say, oh, I support this too. I see this came from that computer down there. Okay, I'm just going to forward it on to the next guy, and it keeps going up and up the chain. The answer comes back, and what happens then when it reaches a name server, the authoritative name servers work like this. Imagine Google has, I'll just say 5 sites. So they have 5 different A records for google.com. Those 5 different A records are associated with some geolocation data that allows their proprietary DNS server to find the right IP address for your geolocation compared to theirs. So how does it do that? How does it know who the client is that made the request, right? Well, the only way it does that is because it sees in the DNS packet the original requesting client in that EDNS Client Subnet packet. It does a comparison and returns the right IP address for the client, not the requesting DNS server. Okay? So they're calling that CDN through DNS, right? We can do content delivery based on DNS. So there's hundreds of domains that do this. Netflix does it, Cloudflare does it. Pretty much everybody that delivers content via what used to be through web content delivery now uses DNS content delivery to make your content come faster. So when the client gets the data back, they get the data that's supposed to direct them to the geolocated site that's nearest to them. So here's what one of these packets look like. This is the information that's in there. You'll see that there's the option code 8, and it tells you the length. The rest of the data, the option data, family, source, scope, and subnet, that's all of the data that's put in the packet. The source netmask is the netmask of the local network. It's supposed to be transferred as a /24 or greater. That's what the RFC says. This is what I got back from Google. /32, right? So that tells me my single IP. The scope netmask is the scope of the A record that was sent back to me, the scope based on my block that was sent to it. And then this is actually the client that was actually doing the lookup at 50 IP address. Here's what a dig packet looks like when you use the plus subnet option. I don't know if you can see it on the screen, but you're doing a dig against Google and you had plus subnet equals and there's an IP address there. That just happens to be an IP address in our Dallas data center. But the interesting thing is in the op pseudocode section, do you see anything different in there than what you'd normally see in a regular query? So the second line, right, it says client-subnet : it's got the IP address, and then it's got the /32, which is the local subnet, and then the net for the answer is in there, right? So it's taking my IP address and passing it up the chain, and it came back in the query. So I know it went through the whole chain and came back without being altered. Does that make sense? Now, in the case of a private IP, I did this from a machine that was behind a NAT, right? So the private IP gets lopped off by the upstream provider, and the WAN IP then gets swapped out and sent on. Okay, so they can't find who you are. Well, who knows about IPv6? Does NAT exist in IPv6? There's no such thing as NAT, right? There's no such thing as private IP space in IPv6. And I want to tell you about a couple things that'll make your hair stand on end here, near the end here, about what's going on with some of the other options. So this is what you get when you see a query that returns a result. You know that upstream server that you queried supports EDNS Client Subnet. So I sent it subnet data and it came back with an answer that says I support it. Now, I'm going to go back. And aside, some servers upstream will bark when you send them client subnet data. Disney was a great one to do this. When this first got rolled out, we deployed this in our cache center to send out for our clients, because our clients are not all in the same area. They're all over the region for each data center. So we noticed all of a sudden when we deployed this that Disney would quit responding to queries. They thought that the data was malformed, so they weren't following the RFC, so we had to do some trickery to make our queries get through to them without sending the client subnet data to them. But it's supposed to be, if you get the data to your server and you don't support it, you just ignore it and move on. So there's two kinds of servers, obviously. There's authoritative servers and services, right? A server, in my mind, is software I can install or a box I can run. A service would be something like Google. recursive and authoritative. The authoritative ones have special proprietary software that allow you to host primary records on their services for geolocation. It's a little bit more complicated, but it works. Bind 9.11 is going to be released, and it's going to support it natively, so you can configure it and manage it through text files, zone files yourself if you want to do that. So once that rolls out, you're going to see a greater proliferation of support for EDNS Client Subnet. These recursive servers all support it now. Unbound, just an aside, who uses Unbound as a DNS caching resolver? You can put your hand up. You're one of the smarter ones. So if you're going to deploy a cache resolver, use Unbound, and here's why. One, they support preemptive cache lookups. So the service actually runs on the DNS server. It monitors the number of queries coming for the various domains that it has in the cache. If it sees a lot of queries, for example, from Google, instead of letting that expire in the cache, it will preemptively go out on the client's behalf and get the new updated data before the TTL runs out, so that the customer doesn't take the hit for the latency on making that work. It's also very lightweight. It has a very small footprint and many fewer vulnerabilities than Bind. So if you're going to use a caching server, it's really the way to go. But the 1.62, the latest release that you can download off of the Unbound.net website, now has built-in support for EDNS Client Subnet. So you configure it and it works out of the box. So this just came out like 2 weeks ago. So you're going to see a huge spike in the number of cache resolvers that transmit EDNS Client Subnet data through the DNS request chain. These other servers support it as well. OpenDNS does. They do some odd trickery. They use two different options in the 22,000 range to send specific information from your particular workstation to their servers if you have the OpenDNS, or what they call it, umbrella client, installed on your machine. So it will actually reveal much more information about the workstation it's installed on than you might want to be revealing. So that's all I'll say about that. Amazon CloudFront also supports client subnet data by default right out of the box. So if you're doing engagements behind Amazon CloudFront, right, doing pen test engagements, and you're using their DNS to do your DNS lookups, do you think that's a good thing? Right, because they're going to broadcast your Amazon IP to everybody in the chain, right? So how do you get around that? We'll talk about that in a little bit, but the basic idea would be you'd build your own DNS server in the Amazon cloud, turn off EDNS Client Subnet, use it for resolution, and it wouldn't forward any data out past your network. So when this first came out in 2011, a consortium was formed called a Faster Internet. Includes all these players here. The problem with EDNS Client Subnet is that nobody has kept a repository as to who supports it, who doesn't support it, both from a primary and from a caching side. So it's very difficult to tell how it impacts your network and how it's going to impact your browsing and your privacy. So this website hasn't been updated in quite some time. As you can tell, because Amazon changed their name to Amazon CloudFront Services now. This is an example that one of the providers put on their website. I stole it from them. The name of where I got it's down there in the bottom. Basically, this just shows how you can send a DNS query all the way around the globe. If that server is answering based on geolocation, it's still going to return the IP address for the nearest content that you're looking for on the internet. So it kind of works like this. The client's in Kansas here. There's these 6 different data centers globally. And the client makes a DNS query. How does the DNS server know which data center to send that client to? And it's all based on geolocation. So in this case, the one that's in Denver would probably be the closest by geolocation, so that IP address would be returned in the A record by an authoritative server that supports the EDNS Client Subnet information. So I'm going to get into a few tricks here for testing. So as I said earlier, there's no registry or repository of providers that support either the caching or authoritative side. Again, the Faster Internet is not current. There's no registry listing for recursive providers either. The services that are coming out, the software, Unbound and Bind, now support it. The Bind is in version 9.11. That's not the mainstream. That's the beta process that they're working on now. So we can use some tricks for testing this, and I didn't have time to take the top one out, unfortunately. The top one here, that dig command, and this has to be done on Windows, unfortunately, because the plus subnet option, when you use the plus subnet option, it doesn't work in some versions of Linux because of the way Bind gets installed. So, an aside, if you want to install dig on Windows, go to isc.org, download the Windows zip file for all the Bind installs. There's nothing to install, just unzip that file into a folder on your computer, like C/dig, and then run dig. Put it in your path and run dig. It'll work. Okay? Much easier to use than NSLOOKUP. So in the first one here, we're actually using a dig against Google, and we're getting a short return. And this domain here, EDNS-Client-Sub.net, is registered, and it was registered by PowerDNS, and for a while they were returning JSON data that gave you a whole lot of insight into what was going on in EDNS. Now, last time I tested this a couple days ago, it didn't work, so I think they took it down, but I'm going to leave it in the slides in case somebody wants it. In the presentation, they may put it back online. The second use of dig here, where you use this plus subnet option, will actually work. So basically dig, you target dig at whatever name server you want to target, and then you just use the plus subnet, add that on there. And if you start to see, one, you'll see the data come back in the option pseudo section, but also you'll see different IP addresses come back depending on the IP address that you put in for the client subnet. So you can, does anybody see a little vulnerability in client subnet just from what I showed you here with dig, right? So you can use dig to tell an upstream provider that you're somebody different than who you really are, right? There's no security in the option subnet that's sent to the upstream servers. So if you wanted to, for example, make it look like your neighbor's browsing porn, use their subnet and start sending a ton of data to upstream providers, right? Somebody might take note of that information being gathered by the upstream servers, and you could do some really strange things with the data that goes out. So what you get back, this again, we looked at this earlier. The important part is in the option pseudo section, you'll see the client subnet data in there. If that's in there, that server upstream supports it, okay? Because here in dig, you're doing a query directly against the server. So if a server is authoritative for a domain, if they are authoritative for like Microsoft, you can query that server for Microsoft.com and it will respond to you. If they're not, if it's an authoritative server and they're not authoritative for a domain, you'll get recursion denied back from that server. You know it's an authoritative server. Recursive servers don't care. They'll just answer for anybody as long as you're allowed to connect to that server. All right, so how can we also test with other ways to test? One of the things that's a really cool tool, if you're familiar with it, it's part of the ELK stack, is the packet beat. Has anybody used that? Yes. So you can install this on your DNS server. Basically, it's a out-of-band network analyzer with several different protocols that are built in. One of them is DNS. It will grab all the DNS traffic. It will parse it out into a nice little packet and send it wherever you want it to go. And in my case, I use Graylog to do it because we already have that built into our environment for monitoring. So we can actually send all of our data from our cache servers and our authoritative servers to Graylog, and we can actually see whether servers are returning the client subnet data in the packet. What you could do if you really wanted to go further, you could create a stream and tag all the DNS messages that have that field in there, and then set alerts on that if you wanted to see what kind of name servers were doing it. I don't know if you can see this real well, but this is a picture here of from our cache servers in an ISP setting. So this is not out of the realm that any ISP could do this, right? So this is there's 4 cache servers that report to this Graylog setup. Those cache servers are all running packet beats, so when somebody hits that cluster of cache servers, the queries come in, they come back, and we're able to filter through to see which upstream providers provide client subnet information back to the requester, which is our cache server, and the clients below it. We can also use Wireshark. We can capture traffic on a local interface or do a TCP dump. What will happen then is we can take that and we can filter that using some of the filters that are in Wireshark. The biggest filter is the DNS option code and the double equals. You can either leave the double equals and the number off and get all of the DNS packets that have option codes in them, or you can search by the number anywhere from 1 through 65335 and see what's out there. So it's a fun little game. You might want to do that with some DNS traffic on your network from time to time to see how that's changing. Note in the data that's included in the RR data is there highlighted in yellow. So that's the kind of information you would see in the Wireshark capture. And I've expanded all that out. So you'd have to expand that out in the view in Wireshark to be able to see it all. Here again is a bigger picture of the same thing. You can see the data that's highlighted there. There is also an Nmap script that somebody wrote several years ago to test for the ability to support EDNS Client Subnet upstream from you. It's kind of limited in its use. It's not really useful anymore since Dig has it built in. You can just do it directly with Dig. It does work, so if you're doing an engagement and you want to check this, you can make it part of a script that you run, see if it works. The last thing here is we can roll our own. We're working on doing a test against the Alexa top 1 million sites to see which ones support and don't support EDNS Client Subnet. Our goal is really to write something that will run on a recurring basis so we can see trends and changes in the implementation of EDNS Client Subnet over time. The problem is we need to run this just on a regular basis, like every day. It takes a while to scan 1 million name servers, and they change, right? The top 1 million change every so often. So we can actually go through and parse out the data, run a Python script to pull out the ECS data and see what trends are happening with that. So why is ECS bad for security? Well, one, it leaks information pretty badly. And again, we're using this ECS Client Subnet, EDNS Client Subnet as an example of the greater problem with option codes in the EDNS0 packets. So it leaks information. Every DNS server in the chain that's touched gets access to your client IP if it wants it. There's no way to honor any subnet restrictions. The interesting thing is all the RFCs, they call for, they spell out very clearly that these are privacy concerns. In the RFC, you can read the text, and they say that they mandate that they have an opt-out mechanism to allow you to opt out of sending this data. How many of you would know, have ever heard your ISP come to you and say, hey, we're doing this, do you want to opt out? Yeah, nobody, right? So the way you would opt out if you ran your own servers, you just turn the feature off. But it's not easy to do. It's built in, and you have to go through great lengths to turn it off. And they're not supposed to send a /32 upstream, but they do. The data can be shared and can be manipulated. Like I told you, you can fake the data that's going to upstream servers, right? So those upstream servers are gathering that data. I'm pretty sure they will, or they are, and probably going to make that data available for sale, right? The data has valid uses. So Google will say, we do this, we track this, one, to give people a faster experience browsing Google, and for us to be able to analyze that data that we collect so that we can scale out our data centers accordingly to traffic coming from different geolocations. That makes sense. But they don't leave it at that, and they don't give you any data retention policy. They don't tell you what they're doing with that data. Now they have the right to sell that data, as do every other provider in the stream. So it's also particularly invasive if law enforcement gets involved, right? Because law enforcement, they're not usually on top of things when it comes to understanding technology. They see a bright new thing. Oh, we got DNA. We can, fingerprint DNA. We can check fingerprints. We can do all these great things, but they don't understand the details and the implications. And if this is not secure, so this data is really kind of meaningless. But you're also going to see things like, I would say, credit agencies, insurance companies, maybe employers buying this information and figuring out who you are and what your browsing habits are. It's kind of scary, right? So, I mean, you may think I'm a little out there saying that, but I can guarantee you it will happen, right? Years ago, who remembers when you got insurance, did somebody ever tell you you had to have a credit check to get your car insurance? That was unheard of, right? Now it's standard practice. It's that same kind of thing. They're using protecting their assets as a way to get at your private data. And the last problem with it is third-party data recipients can, again, buy the data, and they can see what you're doing. And if your DNS provider registers your WAN IP address in their reverse DNS, when you connect on, they can correlate the DNS data that they're getting back to who's connected and what the name is and location and everything else. So it's really not well thought out. The implications of what could happen are not solidified. So I would ask your providers if they're supporting this, not supporting it. One of the other things with the RFC is, remember, to be RFC compliant, you have to support all the RFCs. There's talk of some other options being used, one of them by a rather large company, to ship your MAC address from your device upstream through the DNS chain. So how would you stop that, right? The intent is to use it for good, to attribute infection and malware compromise to a particular device. I don't think they're thinking through the whole process and making it known to people what's going on. So again, to summarize, EDNS Client Subnet has several useful purposes. It does serve some good purposes. It gives people the ability to geolocate sites, provide you a better browsing experience. It enables multi-tenant cache servers to serve up the right data for people based on their geolocation. It has potentials for abuse. And if you get a chance, go look at some of the other EDNS option codes and see what kinds of things are out there. You might be a little surprised at what's going on. And don't let DNS bite you in the ass next time you're doing something you don't want anybody else to know about, all right? So that's all I've got. I think 45 minutes, that's good. Any questions? Leonard?
What do you think is a good way, for me as someone who understands the regulatory multi-currency, won't even know that this happening, right?
Mm-hmm.
I want to protect myself from this. So now I'm not a DNS expert. I have PFSense running at home. Would that be, that's obviously my local resolver, right?
Yeah, so it runs unbound?
What?
It runs unbound inside
Okay.
PFSense, yep.
Okay, so would it be, like, could I stop it within my network, or will the next, like, wherever this DNS request goes through the chain, just take the remote IP?
It'll take the remote IP and do it, right? So, yeah. So if there's not an IP in the packet, or if it's private IP, the next stream outside your WAN, we'll just put in the WAN IP and go forward. So the way around that, you would have to tunnel your DNS somewhere where you knew where it's going, put it to a cache resolver, and then proxy the DNS back out somewhere else. So it's really difficult to keep information from being leaked by DNS.
You have to break the chain somewhere outside of your own network, right?
Yes. Or you have to fake the IP address that's in that option packet, right? Remember I told you could do that? Yeah. Yep. And some of the cache resolvers allow you to specify which servers you send that EDNS data to, but it doesn't matter if the guy next hop up just adds it automatically, right? Which they will. Yep.
There aren't any anonymizers that will serve. Sounds like a business opportunity.
Yeah, it is. It's so new. Remember I said 2016 it was just put in play as an RFC, and there's a whole slew of other drafts out there that are coming. People just are blindsided by this. They don't even know the implications. Yeah, it could be. Yep, definitely. Yep.
Anybody looking at it as more of a defensive aspect? So, like if I run my own authoritative DNS server, now everybody comes to me to look up who my web server is. The minute that I get a request from that end station, that host IP, I get a request for the host name, but I never actually get a connection. Well, why is that dude snooping on my DNS server? He's asking what the IP address is for my web server, but he's not connected to my web server.
Yeah, so there you could actually probably go take it one step further, and if you know that that IP is real, if there was some attribution to it, and you had a list that you knew was a good list of blacklist, you would just not allow that DNS through, right?
Yeah.
But again, there's no integrity in that packet, so you don't know. Somebody could fake it, right? Could be spoofed completely. So, any other questions? All right, well, you got a question?
What about a security mechanism on your own internal network to try to find, make sure you're not being
It's a good question. So you're saying in the DNS, when the DNS traffic goes out,
your authoritative in your own internal network.
yeah, so authoritative servers don't really care about the ECS data unless you're using a CDN network. It's more the recursive ones that would send that out. Right now, Microsoft AD Server doesn't support it, so on the internal side, we don't see it. We only see it on the external side when we get the cache servers outside. But if you send directly to the root servers don't care about client subnet, and they're not going to support it anytime soon. So forward to a known DNS server from your AD server, or forward to the root servers, right? And if you're forwarding to known servers for security reasons, don't forward to the root servers, because the root servers will always answer, right? So I don't know if I answered your question. We can talk about it more afterwards. I don't know if I'm understanding quite what you're asking me, but we can talk about it. Okay. Any other questions? Jackie?
Is there any reason not to write a patch or line?
Be a good thing to do, yeah. You could do that. You could turn it off, but the problem is the next hop up, right? So yeah, what you have to, right? So then you have to inject, you have to inject spoofed IPs into the packet so that the upstream provider doesn't replace that data. Well, the next server up though would add it back if it supports it. Yeah. Because remember, your UDP packet has a header in it that has the IP address that it's coming from. So if the ECS data is not there, it'll just put that in the ECS data to move forward. Yes, sir?
Is there any validation, like if we split that with upstream notice?
I haven't seen that. Nope. Which is a good thought. It should match, right? So the first hop up should see the same IP or the same IP block in the ECS packet as in the UDP header, right? It should match. If it doesn't match, then there's a problem, but I don't think anybody, again, nobody's thought that far ahead, right? DNS is inherently insecure, it's inherently problematic, and so look up this option too if you're into stupidity. Somebody's proposed a DNS API, DNS over SSL tunnel. It's a draft. So, yeah. So imagine if that ever gets put out there. How hard is it going to be then to detect malware via DNS? Just a thought. Any other questions?
So you don't expect any government regulation?
Yeah, you could. Oh yeah, you could. You're getting to my next talk at B-Sides or maybe DEF CON if they take it. So that data could be used by malware, those data packets, to exfiltrate data from your network. They could be used as botnet command and control, right? Because yeah, but in that particular data, they're not doing it. They're typically doing it by text files or by subdomains that are for legitimate registered domains. When they figure out that they can do this, it's going to be very problematic. So, okay. Questions? More questions? So I have a gift for you, Dave. Come on up here. Got a gift for you. Suddenly nervous. Nothing bad. So Dave helped me out last year and taught me a lot of things besides Las Vegas. I figured he's a good Canadian. So tomorrow he's going to go. That was why I questioned you about doing your keynote tomorrow. All right, I'll be around afterwards if anybody has any questions. Thanks. Appreciate your time.